What we're going to talk about here is the idea of the definition of continuity at a point. And this is probably something real foreign to you until I kind of bring it back to you. The question of whether a function is continuous is really a simple one to state. Can you draw the function without lifting your pencil from the paper? Making this idea mathematical is where it's going to become tough. But just to give you an idea of what I'm talking about, let's look at some functions that are not continuous. Or another way of saying that is that they're discontinuous. Here I have a function. This is actually the graph of a rational function. And if I were to try and draw it, I'd start way out here to the left and I'd move in. I'd keep going up. And I'd be going infinitely high along this vertical asymptote. The problem is to get to the other side of the function, I have to lift up my marker here and come down on the other side and now go ahead and try and draw on the other side. Since I'm going to have to lift up my marker here to draw both sides of this, this is a discontinuous function. And it's discontinuous at x equals -2. So anytime I have to lift up my pencil, my marker, or whatever, that's when I run into a discontinuity. Here I have another function. Let me try and draw this one. This looks like a linear function, and I can just draw it, draw it, draw it, draw it, draw it, draw it, draw it. But when I get to 2 here, I reach the open circle. And you'll remember an open circle just means that the function is undefined, so I'd have to jump over this by lifting up my marker here and jumping to the other side and then continue on. Because I had to lift up at this point at x equals 2, I'd say x equals 2 is a discontinuity. In both of these cases, the reason why they were discontinuities is because the function was undefined there. It was either undefined because of the open circle or undefined because there was a vertical asymptote there. Here's a situation where the function looks almost identical to what we had before, except now the function is defined. It's defined right down here at that point. But if I were trying to draw this, I'd get up to the open circle, have to jump down and draw the point, and then jump back up to the curve. I'd have to lift up my pencil to draw this. But unlike the other ones, this one is defined at x equals 2. It's defined to be 3. The problem is we'd really like it to be defined as 4. So if at x equals 2 the value of this function was 4, we'd have that hole filled in, and then it would be a continuous function at that point. But in this case, x equals 2 again is a discontinuity. It's defined, but the difference here is it's not defined to be the right thing. Here we have another situation. We have a graph that if I were drawing it down here, I'd get all the way over here to 1, and then I'd have to lift up and jump up to this other place. Again, this is a function that is defined everywhere. The only place you might be in doubt is at 1, but in this case, at 1, it's equal to 1. My problem is, though, is these two pieces aren't connected up. If I wanted to go ahead and have a continuous function, I'd expect all the pieces to connect to each other, and with this big jump, it doesn't connect up. So this has a discontinuity at x equals 1. And the reason for that is as I get closer and closer to 1, either from the right-hand side or the left-hand side, I'm not getting closer and closer to the same number. From one side, I'm getting closer and closer to 1. From the other, -1. The way I've been saying these things must lead you to believe that this whole idea of being continuous at some point, say x equals c, has something to do with number 1, is the function defined? Number 2, is it defined in the right place? And number 3, does it all connect up the way it's supposed to? And in fact, the mathematical definition of being continuous at a point says that the function has to be defined at that point. So no open holes, no vertical asymptotes. The limit, as you get closer and closer to that point, has to exist. What that means is your one-sided and two-sided limits are equal to the same thing. That tells you that the graph is going to connect up. And number 3, if I do that limit, I get the same thing as if I just put the number into the function. And what that ensures is if I have a graph that comes down here, open circles, saying f of c means that these two pieces are going to connect up. So this is one where number 2 here wouldn't work. That would not exist. But on the other hand, what if they come down and get closer and closer to each other? So now the limit exists, but to make sure that the point falls in the hole there, that's what this whole f of c thing is about. If a function is not continuous at c, then it is discontinuous there. This is all talking about a single point, but in reality what we're typically looking at is over a whole section of a graph, or over a closed interval. If a function is continuous on an interval from a to b, including the endpoints, that means it's continuous all along the interval. That means that I can draw it without lifting up my pencil. And it's continuous from the right on the left-hand side, and it's continuous from the left on the right-hand side. Let me illustrate what I mean by that. Suppose that I have some graph, and we're looking between a point A and a point B. And what we have here is a continuous function. The fact that I just drew that from A to B means that step 1, it was continuous on the open interval. So that means at every single point there, our 3 conditions have held true. The second part says that if we approach A from the right-hand side, what has to happen is it's got to fill in that point. And if we approach B from the left-hand side, it's got to fill in that point. If that's the case, then it's continuous over the entire closed interval. That's the 3 parts. It has to be continuous between the points. It has to be continuous on the left as I approach from the right. So that means as I draw it from the right. And it has to be continuous from the left as I draw it from the left. If that's the case, we're continuous on the closed interval.